VLSos here. This is a video lesson on sigma notation. We're going to start with an example of a problem that uses sigma notation. This is a capital Greek letter called sigma, and it stands for sum. What we have here is a way of generating terms of a series or the sum of a sequence that we would add together to produce a final answer. We use this notation to make the term values that we will add up. How do we use it? We have the expression 2 to the j, and the first value that we're going to use for j is at the bottom of the sigma. J's first value is equal to 0. If we put 0 in for j, we get 2 to the 0, which is 1. The next value of j is going to be one integer greater than 0. The next value of j is 1. 2 to the 1 is 2. And what we do to these terms that we are creating is we express them as a sum. We're going to add them together. Now we started with 0. We then used the value 1. The next value of j to use is the next highest integer value. 2 is next. 2 to the 2 is 4, so we're going to add the next value that we found. We continue with integer values, counting up until the last term that we evaluate or create uses what we call the upper bound, the number written on the top of the sigma. In this case, we put 3 in for j, and we get 2 to the third, which is 8, the value of our last term. This produces a series, and we can now evaluate the series by adding these up. It's not hard. There's only 4 terms, so we'll add this together, and it makes 15. Sigma notation is an algorithm. In general, we have names for the parts of the algorithm. This is a Greek letter. It's a Greek letter S. S stands for sum, and the letter is called sigma. At the bottom, we have the indexing variable, which could be anything, in this case k, and then set it equal to its lower bound, which must be an integer. In this case, k is what we call the indexing variable. A is the lower bound, and it must be an integer. The number at the top, which is the last value that is used, is called the upper bound, and it must be an integer. The mathematical expression that we use to evaluate at those bounds and integer values is a function of the indexing variable. If the indexing variable is k, then this expression must be a function that uses k. We produce a series by putting the lower bound into the function, and we can symbolize that as f at the lower bound a. And then we add function values evaluated at increasing integers. In this case, then, the next value to be used would be a plus 1. And we increase by integer increments until we get to putting in the upper bound b into the function, which produces the last value in the series. The series is called the expansion of the sigma notation. It is all the terms before you add them. And the expansion is a series, and if it followed certain rules of an arithmetic or a geometric series, we may be able to use equations to help us add those terms together. When we do, it produces a sum that we can symbolize simply by a capital S, called sum. The equation that we use to produce the terms is called the argument of the sigma. Let's provide another example. Sigma of the indexing variable n starting at a lower bound of -2 to an upper bound of +2 of the argument n plus 1. We're going to produce the expansion and then find the sum. It's okay to use negatives in the index of sigma. Negatives can be integers. Integers can be negatives. In this case, the first value of n is going to be -2, and the first term in the series will be -2 plus 1, or -1. After using -2, I go to the next higher integer, which is -1. -1 and +1 is 0, plus 0. Then I use 0 to get 1, 1 to get 2, and 2 is the upper bound, so the last term in the expansion is 2 plus 1, or 3. This is series or expansion. I can add it together quite simply. The -1 and 1 cancel out, leaving a 2 plus 3 is 5. So the sum of this series, the expansion of the sigma, is 5. One more example. In this case, it's going to start with the instruction to write a series in sigma notation. We're given the series 2 plus 3 plus 5 plus 9 plus 17 plus 33. And we're asked to make it or turn it into sigma notation, so that sigma notation stands for this series. This can be very challenging. So the approach to problems like this ought to be guess, check, modify. Looking at this, I can see that I've got 6 terms. So my index is going to reflect a sigma notation that will produce 6 terms. I'm going to start with an indexing variable I'm going to choose to be x, and I'm going to start with the first value or lower bound of 1. So if I start with the lower bound of 1 to get 6 terms in the expansion, my upper bound must be 6. Now for the challenging part. What is the argument of this sigma? The argument has to produce these values with this index. So what is the pattern, if any, of the values? With a little bit of thought and some familiarity, this is very similar to powers of 2. Powers of 2, I'm used to seeing 4, 8, 16, 32, and these are close, but always one higher. So my guess is to consider that the argument is going to involve powers of 2, but one more than that, so I'm going to add 1. Now that I have a guess as to my sigma notation, I need to check to see if it produces the series. So I put my first value of 1 into my argument and simplify. 2 to the 1 is 2, plus 1 is 3. I didn't get the first term of my series. It should have been 2, but I got 3, which is the second term. So I'm going to continue to investigate what I've got here. If I put in an x value of 2, it should produce the second term of my series. Let's see. With value of 2, I get 2 squared is 4 plus 1 is 5. So I did get a value, but not the second value. I need to make a change. My argument is producing values that I get, but they're out of order. So the change I'm going to make is to start my index at 0 instead. If my first value of x is 0, I get 2 to the 0, which is 1, plus 1 is 2. So it did produce the first value I expected. I'm on to something. The next value of x is 1, 2 to the first is 2, plus 1 is 3. I got the 3 that I wanted. The next value of x is 2, 2 to the squared is 4, and 4 plus 1 is 5. Everything's good. But I'm in the habit of checking my very last term to confirm that it's 33. My last value is 6. I put 2 in. 2 to the 6th is 64 plus 1 is 65. I overshot it. I expected 33. But wait a minute, I remembered that I had to reduce 1 to 0, so to get that last term must be a 5. 2 to the 5th is 32 plus 1 is 33. I've confirmed that this sigma notation will produce that series. And I did it in the manner of guess, check, modify.